Okay, so Nathan, read me something you have written down about scalar.
I said it's without direction.
What without direction?
Oh, speed without direction.
Speed. What's a better word? That's right, but what's a better word we can use, Celia? A magnitude with no direction. And I'm going to use your example, Nathan, of speed. So that's just like meters per second or kilometers per hour. How's a vector different? Ian, what did you write down for vector?
I said magnitude and direction.
Okay, so magnitude and direction. So give me an example of, Cadence, give me an example of a vector. What? Oh. Marissa, can you give me an example of a vector quantity?
Would it be like displacement, like meters per second squared?
What do you have to be a vector? A magnitude and what's the big thing? A direction. What's the difference between speed and velocity? Direction. So my example here, since he used speed, I'm going to use velocity. And what's my explanation of velocity? This should all be old stuff. What's the shortest explanation you can have of velocity? 3 words. You can tell me what velocity is. Celia? Good, we could say that, or we could even say speed with direction. I figured we needed a little refresher on scalar versus vector. We are totally going to be working with vectors. But it's important that you remember the difference. Now let's think way back to when we worked with vectors before, just simple vectors. Got one question for you. Remember we drew them out and then we did some algebraically. If I have simple vectors in the same direction, what did we do with those?
Added them together.
Yep, so if they're in the same direction, we add together. If they're in opposite directions, remember what we did, Kylie? Yeah, we subtract. That may show up again. When I have 2 or more vectors, and I combine them, do you remember what that final displacement with its direction was called? Like when I had one going this way and then maybe it turned back this way and we had this part that was left over, how did we label that?
The result.
Good. So the resultant is what is, or what we're talking about. And we just call that the sum of 2 or more vectors. We've had that word before. A new word that we'll use this time is something called the equilibrant. The equilibrant will say it cancels out the resultant. Oops. And how it does that is, it is equal in magnitude, but opposite in direction to the resultant. So let's say R equals well, I'm just going to make something up here. 17 meters per second at 0 degrees. I'll make this one pretty simple. Then my equilibrant would have the same magnitude, 17 meters per second, in the opposite direction. How do I find the opposite direction? Jaden, do you know how to do that? Who else is out there? Marissa, would you know how to find the opposite direction?
Would you just do 180?
Yeah, whatever this number is, to get the equilibrant, it's like R plus 180 always. So this is pretty easy. 180 degrees. So if you're asked for an equilibrant, you use your magnitude, you add 180 to get your direction. There will be some problems where you have to do that. Make sense? So try this. If my resultant is 13 kilometers per hour at 135 degrees, get your calculator out and find your equilibrium. Raven, what's the equilibrium?
13 kilometers per hour, 315 degrees.
At what?
315.
Good. Easy enough? All right. So you remember when we did all that stuff graphically and you drew everything out with the arrows, and it's really not very fun. So now we're going to use this with projectile motion, only we're going to do it mathematically. We're not going to draw it out. But we have to start with the basics and work our way up to projectile motion. So this would be non-graphical addition of multiple, it won't always just be two, multiple vectors. And really it could also just be called sometimes two-dimensional motion. And we're going to solve using what's called, and you should have seen this in Algebra 3 or Honors Algebra 2 probably at some point. If not, definitely in pre-calc, only this is like super easy. This particular formula we work with to begin with, I believe, comes back to even geometry maybe, parts of it. It's called the triangle method of solving vectors. Or it might be called also, it could also be called here, adding vectors. So I want you to see those words so then if you see them later when you have to work a problem, you'll know what you're being asked to do. So this is going to allow us to work in 2 dimensions. What would those dimensions be? When you think about all the formulas we've had so far, what have we been calling those components? We've always had one or two had to do with their direction. What do I call the vertical component? Or what have we been calling it? Y. So this would be Y, and if I'm not in Y, what would I be in? X. And it really is a way to simplify motion, to look at its parts. So we're going to go part to whole. It'll let us do that. Okay, so I'm going to work you through two different types of problems. And we'll try to be really clear about what they are. This would be problem type 1. And this is how you figure this out, what kind of math you need to use. First of all, in this one you will be given two vectors when the resultant is found, you form a right triangle. So let's think about this. I want to see if you can come up with what you need. In these problems, the two given will be one in the x direction, one in the y direction. So you form two legs of the triangle. The third leg is your resultant. Obviously, this is your x component, this is your y component. Do I need to make that bigger? Can you see it? These are easy. Anybody know what formula we're going to use to find R? I've got a right triangle and I'm looking for, what would this leg of the triangle be called? Hypotenuse. You remember that from geometry? What? Yay, the Pythagorean theorem. We're going to use the Pythagorean theorem. Which is c squared equals a squared plus b squared. You should all remember that. Now let's look at what that looks like in physics. This is my r squared equals x squared plus y squared. It's the same thing as Pythagorean theorem. It allows us to find our hypotenuse. That's okay. Yes. You want to get him? You want me to get him before we get him? So pretty simple. Get your little formula cards out and add that one to it. You're fine. And if you don't have your little formula card, put a box around it like I did and go back and do it later. Okay, so this allows us eventually to find R. This is the magnitude of the resultant. Make sense? Any questions? You guys are so quiet. You weren't that quiet when I had to run to the office. So that allows us to find R. Where was I? To find the direction of R, we use something called the tangent.
This would be a little high.
Oh, wow, you guys want to see that?
Yeah.
Sorry. Okay, so we're going to find the direction of R. And when we do that, we use something called the tangent inverse function, which you should have learned in math, but I don't know if you'll remember how you do that. If I have a right triangle, my tangent equals a ratio of what? 2 legs. Remember this? Well, I don't want to do that yet. My tangent is, when I talk about legs, it's a ratio, right, of opposite to adjacent side. If I want to find my angle, I use what's called the tangent inverse function. Look at your calculator for a little bit. You may or may not have used this in math yet. But if you look and you find tangent, above it says tangent -1. That's what it looks like on your calculator. When you want to use that function, you have to hit your second key and then hit that. So when I want to find the angle, I end up with tangent to the -1 over, or multiplied by opposite over adjacent. You remember that from geometry? SOHCAHTOA. If I want to know sine, opposite over hypotenuse, cosine, tangent, that should be a little blast from the past. So this formula, I believe you're also going to want on your card, or at least to circle it. And just in case you need to see it, I don't think you do, but there's your right triangle. So when we're solving this, we're looking for this angle, the angle of the hypotenuse. Any questions about how that looks? Anybody need to write it down? If you do, I'll wait a second. For some of you, it's probably been a little while. In fact, you're going to use each of these later, so. We good? All right. So let's put this, I'm just going to do one problem and then I'll let you work on some, maybe two. Put that problem in your notes. Okay, everybody got it? All right, so let's look at this first. Sometimes when you get these problems, especially something like that, it's good to kind of draw it out. So I've got a pyramid. And I've got someone actually hiking up the side of this pyramid, right? They wouldn't climb directly up. But when I do this, I have to think about it in terms of x and y. So here's my y, here's my x. And I know that my width is 230 meters. And I know that this is 136 meters. And I know that I want to find this, and I want to find this. I want to find my angle. It's a question mark, and I want to find my resultant. That's a question mark. So I'm going to use my r squared, whoops, not cubed, equals x squared plus y squared. So r squared equals, ooh, what is my x? What? Oh, you want me to write it bigger? Would that, can you just not see the whole thing, or is it too small? Okay, let me rewrite it so it's big. You're welcome. This is my r, which I want to know. And this is my theta, my angle that I want to know. And then this would be my y. And my y is 136 meters. And so I'm going to use r squared, because I've got the two legs, equals x squared plus y squared. Now there's only one little trick in this. I know directly, because it's straight, that my y squared is 136 meters squared. What quantity would I need to use for x? What? Yep, I need to start with this, but if I want to know the height, what do I have to do with this? Would you say, Jaden? Yeah, divide it by 2, which is what, 115? Okay, so this is 115 meters squared, and all of that equals r squared. So work through that. We'll see what we come up with. This is 13,225, and it would be meters squared, plus, what is that? 18,496. Still meters squared. When you do the math, anybody have written down what r squared equals yet? The whole thing? I'll wait till you get there. You really probably should be writing this down, or you're not going to know what to do later, probably, some of you. What's my total r squared? What you got, Celia? 721 what? What are my units at this point? Yep, meters squared. So then I can just take the square root of each, and I have r equals, what does that come out to? 178 meters. Now, what should it be in sig figs? When you read the problem to begin with, 136 has 3, 230 only has 2, so it should be 180 meters. So we know this is 180 meters. We know our x now, we figured out it's 115. So now I want you to see if you can find your angle, which is equal to tangent inverse times opposite over adjacent, which would give me tangent inverse, what would that be, 136 over 180. Sorry, I started writing little again. I'm going to write this bigger, 136. So put it in your calculator, tangent inverse function, 136 divided by 180. And that gives you the angle. Let me know what you get. See if it matches mine. What you got, Callie?
I got 37.1, but then 6 makes it just 37.
Yeah, you can round. You can round most of the time your angles just to a whole number. So I would write this whole thing as R equals 180 meters, 37 degrees. Then I'm going to ask you, even though it wasn't part of the question, to give me the equilibrium. Jaden, question?
Isn't 180 the hypotenuse?
Yeah.
I think we did opposite adjacent. We did.
Oh shoot, did I write the wrong?
We did opposite. We did opposite hypotenuse.
Oh. We did. So this should be 115, shouldn't it?
Yeah.
Whew, thank you. Let's fix that. I apologize. I tried to do it from memory, and I didn't have a very good memory. So what did we get? Yeah, Paige said it. So let's write it over on another sheet of paper. Just so we make sure you got it right. I apologize. Okay, so then when we did that, theta equaled 50 degrees. So I would write R equals, now I can write that, 180 meters, 50 degrees. Now tell me what the equilibrium is. See if you can do that. What should my degree reading be, Kara?
230.
What?
230.
Good. Got it? All right.